Hey, what's up, Chem Peeps? What in the heck are we gonna do in this video? We're going to interpret acid-base titration data. As always, breaking it down. In this vid, we're gonna look at acid-base titration curves for not a strong, but a strong-weak combination in order to explain the relative concentrations of each species along the curve, so we can then calculate the pH at any point along the titration. Now, as you take a look at your screen and in your notes, I'm first going to work you through the titration of a weak acid with a strong base. And I want you just to focus on what is in the beaker at the particulate level. And then we'll come back and talk about how to calculate the pH as we perform the titration. Now, in this example, our analyte is a weak acid. That's what I'm starting with in this beaker. And we can recognize this is a weak acid because mostly everything in this beaker is the original weak acid molecules. It hasn't really ionized all that much, and that's described by the equation here. Now, as we perform this titration, it's also important to keep in mind the neutralization reaction to describe this titration. And I've done it in two ways. I've got the molecular equation here, and the net ionic equation for a weak acid strong base titration right beneath it. They represent the same thing. I just eliminated the spectator ion, which in this case is just the sodium ion. So notice initially my pH of my weak acid solution is in the acidic range, which makes sense. It's an acid. Note that it's not as acidic as we saw with the strong acid in the strong acid strong base titration earlier. All right, I'm gonna start dropping in some base. As I add my strong base, notice that I use up some of my weak acid to form some of its conjugate base. It's important to note here that the conjugate base is not a spectator like we saw in the strong acid, strong base titration. It's contributing to the pH, and therefore I have not graded out. So again, there's really two different equations you want to be thinking about here. The reaction of that weak acid with water, and the neutralization of that weak acid with any added strong base. Let's keep going. Used up more weak acid, formed more conjugate base as I added more of my sodium hydroxide, my strong base. Let's keep going. At this point, I've added enough strong base to use up half of my weak acid. Note that the concentration of my weak acid and conjugate base are equal. And this is an important point along the titration. This is known as our half equivalence point. We're halfway to neutralizing all of our acid. It's also important because at this point, because the concentration of weak acid and conjugate base are equal to one another, the pH of our solution at this point is equal to the pKa of our weak acid. We'll talk about that more in a minute. In the meantime, let's keep adding more strong base. Continue to use up more of my weak acid. Now the conjugate base is in greater concentration. Adding more. Oh my goodness, I've used up even more of my weak acid, producing more of the conjugate base. At this point, I've used up all of my weak acid, converted it all into its conjugate base form. I've neutralized all of the weak acid, and I am now at the equivalence point. But importantly, we are not at a pH of 7, because the conjugate base ion that forms, the salt that forms, is not a neutral salt. The anion of that salt, the conjugate base, is going to contribute to the pH. So notice that the pH in this case is slightly basic, not pH 7. If I keep going, notice that we have a huge jump in pH. What's contributing to the pH here is that strong base. It's overwhelming any contribution to the pH by that weaker conjugate base. And if I keep going, it's just going to continue to be that strong base that's going to determine what's going on with the pH of my solution at this point. But let's jump back, restart, and think about the calculations that we would have to do along the curve. If we've got a weak acid initially, before we've added any strong base, how do I determine the pH? Well, we're just going to use our weak acid in water equilibrium and set up an ice table. Perform your ice table calculation. Many times you can do the X is small approximation to make the math a lot easier. You can then solve for the hydronium ion concentration and use pH equals negative log of hydronium ion concentration to determine the pH of your initial acid solution. Once you start adding strong base though, you've converted some of your weak acid into its conjugate. We have weak acid and its conjugate base both in solution, which means we've got a buffer. So you will use a buffer calculation to solve for the pH at this point, recognizing that you've got both weak acid and substantial amount of conjugate base. And so both of them are contributing to the pH of your solution. Yes, there's some ionization of your weak acid to form hydronium, but the conjugate base is also reacting with water to form some hydroxide. So you've got to do a buffer calculation. I think the easiest way is to rearrange your Ka expression to solve for the hydronium ion concentration, focused on that ratio of weak acid to conjugate base. As I continue to add more strong base, I use up more of my weak acid and form more of its conjugate base. I continue to use the buffer calculation to determine the pH of my solution. Again, keeping in mind that the concentration of our weak acid is continuing to decrease and the conjugate base concentration is continuing to increase. Therefore, even though this is a buffer solution, our hydronium ion concentration is slightly decreasing. And then we get to the half equivalence point. Remember, this is an important point along the titration because we have equal concentrations of weak acid and conjugate base. And so as you look at the buffer calculation that we would perform at this point, because the two concentrations of our weak acid and conjugate base are equal, look at what happens in the buffer calculation. Anything divided by itself is 1 and will drop out of the calculation. Therefore, at this point, whatever the hydronium ion concentration is, it's equal to the Ka of your weak acid. Or whatever the pH of the solution is, that is the pKa of your weak acid. Oh, magic! As we keep going, notice that now it's the conjugate base that dominates in solution. It's still a buffer because we still have both components. The only difference is now that conjugate base is dominating and your solution continues to get more and more basic. One more time, more strong base added, using up more and more of our weak acid, forming more and more of the conjugate base. Still a buffer though, as long as I have some of each the weak acid and conjugate base. And then we get to this point, the equivalence point. Yes! Here, we used up all of our weak acid. The only thing that's in solution, we've got water and a salt. But remember, the anion of that salt, our conjugate base, is contributing to the pH of our solution. And so at the equivalence point, you can think of your solution as a bunch of conjugate base. Now your conjugate base is a weak base, and therefore, in order to solve for the pH at your equivalence point, you're simply going to use another ice table. You set up your ice table to solve. Some important things to keep in mind. Again, you can typically do the X is small approximation to make the math a little easier, but also remember that this is a weak base, so you'll be using the Kb value and you're solving for hydroxide ion. And that's important and a common error that students make. Beyond the equivalence point, we've added so much strong base that we've used up all of our weak acid, and now our strong base is in excess. And that is what's dominating, what's really contributing to that very high increase in pH. So that's all we really need to focus on when it comes to determining the pH after the equivalence point. Determine the excess number of moles of hydroxide ion that you've added. Determine the total volume of solution. Remember, as you are adding more and more strong base to your beaker that you're doing the titration in, your volume continues to increase. And then, again, important to remember that you're working with a base, hydroxide ion concentration, and not hydronium ion. So, to recap, one more time for the people in the cheap seats. And keep in mind, have a fantastic day.